Happening right now, all across the power grid that surrounds us, there's this constant, invisible battle being fought. It's a massive struggle between the immense power that runs our lives and the delicate electronics we depend on every single second. So, what's standing in the middle? Let's find out.
I mean, really think about it. What is it that protects your phone, your laptop, your whole digital life from the raw, untamed energy that's flowing through the power lines just outside your window?
Because on one hand, you've got the sheer scale of the power grid, massive, complex systems just like this. And on the other, you have the microscopic, delicate precision of the electronics we use every day. These two things, well, they're fundamentally at odds with each other. And that tension, that's where our story really begins.
All right, let's dive into the grid's hidden danger. We're talking about what happens when voltage goes rogue. The technical term for this is a transient overvoltage. So what exactly is that? Well, a transient overvoltage is a really brief but incredibly powerful surge of voltage on an electrical system. The best way to picture it is to think about a water hammer, that sudden, violent pressure spike you can get in a water pipe. It's this unexpected, powerful shock to the system, and it can cause some serious damage.
And where do these attacks come from? Well, they come from two main sources. You've got the man-made events, like something called capacitor switching, and then you have the raw brute force of nature itself, lightning.
Let's tackle that first one, the man-made surges. You could almost think of these as the grid's own inside jobs. And believe it or not, some of the biggest culprits are just routine operations. See, the grid uses these huge capacitor banks. You can think of them as quick charge energy reservoirs to make everything run more efficiently. But just flipping the switch on one of these things can send a literal voltage tsunami racing down the power line.
And wow, this is what that tsunami actually looks like. This waveform shows the exact moment a single one of those capacitor banks gets turned on. You see that massive initial spike? That's the overvoltage. And it's followed by this chaotic ringing effect as the whole system just struggles to get stable again. It's an incredibly violent, high-frequency event.
But there's another, much stranger kind of internal threat out there. It's called ferroresonance, and it's a real troublemaker because it can result in these super high voltages and currents. But the waveforms it creates are just completely irregular and chaotic. It's a much more unpredictable beast. And these graphs, they show you the split personality of ferroresonance perfectly. Over on the left, you see its unstable, chaotic state. The voltage is just all over the place. It's a mess. But then on the right, you see how it can suddenly just settle into a brand new, stable state that is dangerously high. It's that sheer unpredictability that makes it so tough to handle. Okay, so that covers the inside jobs. Now let's talk about the other side of this battle, nature's electrical fury. We're talking about when lightning strikes the grid. Now, you might think lightning is pretty straightforward, but it can attack in two different ways. A direct strike is, well, it's exactly what it sounds like. Lightning physically zaps a power line. But the much more common threat is something called an induced surge. And this is where a nearby strike creates a massive voltage spike on the line without ever actually touching it. So how in the world does that happen? It's a super fast three-step process. Okay, step one, a negatively charged thundercloud drifts over a power line. Through electrostatic induction, it actually pulls an opposite, positive charge up onto the wire and just holds it there, trapped.
Step two, the cloud discharges its energy somewhere else, maybe to another cloud, maybe to the ground a mile away. Now this is the crucial part. The strike does not hit our power line. The trap has been set.
And finally, step three, the trap is sprung. The moment that cloud discharges, it instantly lets go of that positive charge it was holding on the line. And with nowhere else to go, that charge just erupts, shooting down the power line in both directions as two incredibly powerful surge waves. It's an attack without a single touch. So how do we possibly fight back against all this? Well, let's talk about taming the transients. We're going to start with how engineers have figured out how to design the perfect switch.
For those man-made capacitor surges we talked about, engineers have a whole bag of tricks. They can use something called synchronous closing, which is basically timing the switch to flip at the absolute perfect microsecond in the AC cycle. Or they can add pre-insertion resistors that act like a shock absorber to dampen that initial spike. They can even just change the capacitor location to add more of a buffer or stagger the switching times so you don't get multiple surges at once. It's all about controlling that initial tsunami.
But what about the surges that still get through? Like from lightning? That brings us to our final line of defense, our invisible shield. These are the grid's bodyguards. And the philosophy behind overvoltage protection is actually pretty simple and elegant. First, you have to limit the voltage that can even reach your equipment. Second, you divert the dangerous surge current away from it. Third, you can try to block it entirely. And finally, you bond all your grounds together so there are no voltage differences. It's a defense in-depth strategy. And this right here is a brilliant example of one of those principles in action. This is an isolation transformer. See that grounded electrostatic shield right there in the middle? It basically acts like a bouncer at a club. A high-frequency surge comes in, it sees that shield as a super easy path to ground, and it gets diverted away before it can ever cross over to the protected side. It's like creating an electrical safe room for your gear. But the real heavy lifters of the grid are the surge arresters. You can think of these guys as high-speed, heavy-duty pressure relief valves for electricity, and they come in a few key types. You've got the classic technology, which is really durable but a little slower. Then there's the modern MOV, or metal oxide varistor, which is incredibly fast but a bit more sensitive. And of course, engineers have combined the two to get the best of both worlds, speed and durability. Each one has a specific job to do in this invisible shield. So the key takeaway here is that this invisible battle, this constant fight between these powerful surges and our network of defenses, it's happening all the time, every second of every day, to make sure our power and our entire digital world stays stable. So the next time you're in a storm and the lights flicker for just a second, will you think of the surge that just raced down the line? Or will you think of the invisible shield of arresters and transformers that stood in its way and protected you?